Wind turbines are giant power producers, a fantastic way to generate sustainable energy without ruining the planet. Inside that big white shell at the top, there is a whole system of components. They all work together to turn the slow rotation of the blades into fast usable electricity. Wind turbines can produce enough electricity to power hundreds or even thousands of homes, depending on its size and location. Even though these massive machines look solid and unshakable, trust me, they shake a lot when it gets really windy. And that's why we, as engineers, need to do some serious calculations before building one. One of the key things we focus on is vibrations. Wind turbines have their own natural frequencies. If an external force like wind happens to shake it at the exact frequency, it can trigger resonance. And trust me, for huge structures like turbines, resonance is bad news. So in today's video, we're going to see how a wind turbine behaves across different vibration modes and natural frequencies. And in the end, we will see what happens when we reach the resonance zone. Here is the 3D model in SolidWorks, and let's start by creating a frequency study. First, I want to assign the material to each part of the wind turbine. Then, I will fix it from this face, just like it would be fixed to the ground in real life. Now, by default, SolidWorks gives us the first 5 modes. But let's by step. I wanted to see how this turbine behaves in 15 different vibration modes. So let's increase the number of modes to 15 so we can see more dramatic behavior. And now we can run our simulation. And there we go. These are our results. 15 modes, each with its own frequency and vibration shape. And let's take a closer look right here. Mode 1 and 2 are very low, just 0.447 Hz. Slow structural movement. But as we move up to mode 6 to 10, you can see the frequencies increases rapidly. Things get shakier. By mode 15, we're already at 5.28 Hz, which is a very high vibration. Now let's talk about resonance. Based on this turbine design, we calculated that the operating frequency should be around 2.8 Hz. And look at mode 13, 2.88 Hz. That's dangerously close to our operating frequency. If we operate in this zone for too long, resonance will kick in. Now let's take a moment to compare mode 1, 3, 13 and 15. In the first mode, where the frequency is low, we see a basic sway, no major deformation on the blades. Then moving to mode 3, with slightly higher frequency, the blades start to show a bit more movement. Then in mode 13, we enter the resonance danger zone, and you can clearly see the sharp deformation on the blades. Finally, for mode 15, it shows the most intense and rapid shape changes, especially around the blade tips and tower top. And to really see how each mode deforms the turbine, let's go back and animate them. Starting with mode 1, the movement is slow and smooth. The whole structure gently sways. Then comes mode 13. Let's animate it. Right around the resonance frequency, you'll notice the blades start to deform heavily and rapidly. And finally, let's animate mode 15, where the vibration is fast and intense. We can notice complex twisting at the top. These animations really help visualize how dangerous resonance can be if it matches the turbine's natural frequency. So behind these calm spinning giants is a whole lot of engineering magic. That's why doing this kind of analysis is critical when designing real-world turbines. If you enjoyed this breakdown and want to see more engineering simulations, don't forget to like, comment and subscribe. See you in the next one.